Hey, what's up, guys? This is Sheng here. So today, let's take a look at LeetCode problem number 131, palindrome partitioning. Given like a string s, partition s, such that every substring of the partition is a palindrome. Okay, and then return all the possible palindrome partition of s. So I believe all of you should have known what is a palindrome, right? So palindrome means that, A, B, B, A is a palindrome. Basically, the string will be the same after reversing the string, and then that's a palindrome. But for this problem, it not only it asks you to check the palindrome, but it also asks you to return all the possible palindrome partition of S, where each of the partition is also a palindrome. And notice that a single letter is a palindrome for sure. That's why for this AAB here, we have two output here. The first one is AA and B, and then AAB. But A and AB is not, because AB is not a palindrome. Okay, so I mean, for this kind of question, ask you to return all the possible numbers. We usually use the backtracking or the DP, right? And for this kind of like you have each of the possible ways of partition these things here, right? So we usually use a backtracking. Basically, the backtracking method will be the first one is the first backtrack, right? So the first parameter is always the start index, right? Where it's telling us where should we start, right? Basically, it means that we have we have figured out all the we have partitioned all the strings before the start. Now I'm going to try the partition from here onward, and then we have gonna have like a current partition, right? Current partition means that what is the current partition list here? So so the logic for the backtracking will be what? Starting from the start index, and we're gonna try each of the substring, right? From start to what? To end, and we try all of those partitions, the out of substrings. If the substring is a palindrome, then we know, okay, that's gonna be one of our candidate. We can just move the start to the index that's after the after this new palindrome string, and then we're gonna add that new string to this partition list here. And in the end, if we reach n here, the start is equal to n, then we know, okay, we have find the answer, one of the list where each of the item is a palindrome string, right? And that's the basic backtracking logic here. And actually, to improve the time complexity when checking if the substring that from start to end here is a palindrome, we can pre-calculate it. We can pre-calculate all the substrings, right? We give all the substrings a Boolean value, which indicates if that substring is a palindrome, so that here we can just simply use O1 time to get to check if that substring is a palindrome or not. Okay, and to do that, I'm going to use like a DP, right, to check the palindrome. I think that's going to be to populate all the flag to check all the substrings. If the substring is a palindrome, we use a DP, right? And cool. So let me try to implement that DP here. Maybe I'll try to explain a little bit more why I'm implementing that. So I'm going to have like a DP, right? So at the beginning, all the elements is false, right? So equals to n for this in range n, right? Because I'm creating like a 2D array here whose size is n here to and this dp I and j. dp I and j means that from I to j, if this thing is a palindrome, the value is is true, either true or false, and that's the definition of the dp here. Okay, and the way we're checking it, I believe in LeetCode there's like a similar problem. Just ask you to check if a string is a palindrome, and we basically use the same logic here. So I'm looping through the I from back to the start. So the reason being is that I want to use the I and j, start from I and ending j. That's why I loop from the end. And then for j I loop from I to n. Okay, that's how I loop through this. I give the value for the I and j here, right? Because from I to j. Okay, and the logic is pretty straightforward. I mean, if the si is equal to sj, right? Because to check the palindrome, let's say we have a, b, b, a, b, and a. Let's say if this is I, and if this is j, it can the substring the substring I to j can only be a palindrome when it could be a palindrome, right? Might be a palindrome when the si is equal to sj. This is the case. Otherwise, if we have like b a a b a, and this is I, this is j, so the I and j is not the same, then it cannot be a palindrome, right? So we only assign this dp to true. First condition is the si has to be equal to be the I has to be same as sj here, right? And then if si is equal to sj, and then all we need to check is that if the dpi plus 1 and the dpj minus 1, if they are the palindrome, right? If they are the palindrome, and then the current one is also a palindrome, right? So, and another case is that if the j minus I is smaller than 2, right? So this is for the one letter case and two letter case, right? So for this case, two cases, as long as the I and j are the same, and j minus 1 is smaller than 2, then we can simply assign this flag to true. Or like I said, or the dp I plus 1, okay, and j minus 1, right? And j minus 1, and then we assign the dp I j to true, right? And after this one, we have store all the flag for each of the substring. Okay. Then we're gonna have like an answer equal to this one, and then now it's time to define our backtracking functions, right? So like I said, the backtracking, the first one is start index, and second one is a current partition. Partition. Okay. And then here we call the backtrackings. We start from 0 and we pass in an empty list, right? And then we return the answer. So the, the base case, right? So when the start is equal to n, we know that okay, we have traversed to all the strings, and we have processed all the strings, right, before the start, which means that each of the substring in this current partition is a palindrome. Then we can simply do a append with the current partition, right? I do a deep copy because this is going to be the reference, right? That's why I do a deep copy of that. And what's and for I in range of start to n, right? if dp start to I is true, right? It means that if that's a palindrome, then we can update the partition with the substring. Actually, to further improve that substring, the string slice, I can just use a current string here. So every time when we are at the new index here, we can simply do a append this thing to the end, so that we can improve this one by changing this time complexity by getting a substring to O1 time instead of ON time, right? And then we have a partition append to the current string, right? And then since this is a backtracking, it means that we're gonna remove that partition dot pop, right? And then right in the middle here, we have what? We have backtracking, right? Since we're at I here, which means that the next index starting point will be I plus one, right? And then we pass in this current partition. Yeah, right. So only continue if the sub string is palindrome, right? Palindrome. Okay, cool. I think let me try to run this code right here. Name partition. Okay. Okay, so this one accepted. Let's try to submit. All right, so it passed. Yeah, let's see what's next. And to calculate the time complexity, so this one is a little bit complicated because, so first, right, we have O of n square here, right, to pre-calculate all the palindrome flag for all the substrings. And so the tricky part is this backtracking part. Basically, we're what? We are trying to get all the substrings. We're checking all the substrings, right? And for each of the, sorry, basically we're checking all the partitions. And for each of the partitions, we're checking if the string is a palindrome or not. And let's say we have a, right? So what is the total what is the total partition for this kind of string? You can think it in this way, right? So you can split the string on each of these locations, right? So how many places we have? We have n minus one. And at each of the places, you have two options. You either cut from here or you don't cut from here. So which means that the total combination for this one is going to be the 2 to the power of n minus 1. And that's the total number of the partitions we have. And for each of the partitions, right? For each of the partitions here, we're gonna loop through. Basically, we're gonna try to check if they are if this string if they are the substring, right, of this partition combination, they are palindrome, and that will take an O(n) time. So that's why the total time complexity for this problem is like what? It's 2 to the power of n, right? Since this n minus 1 will be 2 to the power of n and times n. Yeah, so that's going to be the time complexity, right? So the space complexity is the same, right? I think the space complexity is going to be the 2 to the power of n, which will be the total number of the backtracking, because we'll be using that many of the backtracking stack recursive call, right, to check that. Cool. I think that's it for this problem. I think it's a pretty pretty interesting. Like I would say it's called a backtracking plus DP combination problem. Yeah, I hope you guys like it. All right, I'll just stop here. Thank you so much for you guys to watch this video and stay tuned. I'll see you guys soon. Bye bye.